In this video, we'll look at an experiment that demonstrates spatial superposition using light. It requires 4 mirrors. The first and last are semi-transparent, while the 2 in the middle are ordinary mirrors. We'll also need a light source. Now we shine laser light onto the first semi-transparent mirror, which will then split the light into 2 beams. In our setup, 50% of the light gets reflected and goes downward, while the other 50% is transmitted and continues upward. Then, the light beams reach the top and bottom mirrors and get reflected. And finally, they meet at the second semi-transparent mirror. Now, if we have set up the mirrors precisely as drawn here, all the light will go upward in the end. Although the outcome may seem surprising, it can be fully explained by classical wave optics. In fact, this experiment was already done with non-laser light in the late 19th century. But now, we'll do a series of experiments whose outcome will look not only surprising but outright impossible. We'll send only a single photon, the elementary particle of light, often called the quantum of light. The photon reaches the first mirror. It's not obvious what will happen next because the photon is an elementary particle and cannot be divided 50-50. There's no such thing as half a photon. But a couple of nanoseconds later, the photon comes out above the last mirror and continues upward. You can repeat the experiment many times. The outcome will always be the same. So the question is, which path did the photon take while it was between the mirrors? Since the photon is guided by the mirrors, we can think of 2 possibilities. The first possibility is that the photon took the red upper path. Let's do an experiment to find out. We can observe that if we place a piece of glass of a specific thickness in the upper path, the following happens. We send the photon, and then, a couple of nanoseconds later, the photon comes out below the last mirror and continues downward, always. Remember, without the glass, the photon would have come out above the mirror, not below. So the glass has made a difference, which means it must have interacted with the photon. Therefore, the photon must have taken the upper path. It seems we are done, but just to be sure, let's do another experiment. The second possibility we can think of is that the photon took the blue, lower path. So now, we place the glass in the lower path. We send the photon. And again, it comes out below and continues downward, always. We can use the same argument as before. The glass has made a difference, so it must have interacted with the photon. Therefore, the photon must have taken the lower path. So the results of our experiments show that the photon was somehow traveling along both the upper and lower paths at the same time. This is the only reasonable conclusion because we were able to interact with the photon on both paths using the glass. And now let's see how quantum mechanics explains this phenomenon. The photon reaches the first semi-transparent mirror. Since it is an elementary particle, it cannot be split in half. But nature has an ingenious workaround. It is called superposition. According to quantum mechanics, the photon enters a so-called spatial superposition state, where it is traveling simultaneously along the upper and lower paths. In a sense, it is in 2 places at the same time. That's why, in the previous experiments, the glass could interact with it at either location. Now, the photon will reflect from the mirrors. And finally, the second semi-transparent mirror recombines the 2 branches. And according to quantum mechanics, it can be calculated that after leaving the apparatus, the photon will no longer be in superposition.